The research paper introduces the concept of p-wave magnetism, a counterpart to p-wave superfluidity in superfluid 3He. In conventional wave superconductivity, the U1 gauge symmetry is broken by the Cooper pairing instability of the Fermi surface, while preserving the crystal-lattice symmetry. In contrast, p-wave Cooper pairing in 3He breaks the parity symmetry, resulting in extraordinary properties. The authors identify the realization of p-wave magnetism in CeNiAsO, demonstrating strong parity breaking in anisotropic symmetry lowering of spin-polarized and time-reversal symmetric Fermi surfaces. The authors' approach sidesteps the unavailable exact solution of the many-body interaction problem, instead focusing on suitable non-relativistic crystal lattice and spin symmetries to promote anisotropic symmetry lowering of the spin-polarized energy isosurfaces. This approach leads to the identification of unconventional p-wave magnetism in CeNiAsO, accompanied by an additional anisotropic distortion. The paper highlights the significance of non-relativistic spin symmetry groups in identifying materials with oppositely shifted off-centered energy isosurfaces with opposite collinear spin polarizations in momentum space. The authors discard collinear magnetic orderings in real space crystal structure, instead focusing on non-collinear coplanar non-centrosymmetric magnets with a non-relativistic spin symmetry, C2 up TAC, T. This symmetry, combined with the non-centrosymmetric magnetic crystal structure, allows for a compensated magnetic phase with zero net magnetization and a momentum space energy spectrum satisfying parity breaking and time reversal symmetry. The authors present a minimal Hamiltonian model for a p-wave magnetic lattice that fulfills the specified spin symmetry criteria. The model Fermi surface and band structure exhibit p-wave modulation with a single spin-degenerate nodal line, fulfilling the predicted symmetry requirements. The authors predict a large spontaneous anisotropy of the resistivity as a readily detectable experimental signature of this unconventional magnetic phase. Overall, the paper opens new prospects in fields ranging from topological phenomena to spintronics, identifying abundant and robust realizations of unconventional p-wave magnetism without requiring strong correlations and extreme external conditions. The research paper discusses the unconventional p-wave magnetism in CeNiAsO, a material candidate with a realistic band structure and resistive anisotropy. The magnetic crystal structure, reported experimentally, features an alternating stacking of quasi-2D layers of CEO and NIAs, with both layers taking the PBO crystal structure. The spin space group contains the C2Z T0.5a symmetry, fulfilling the symmetry conditions for the unconventional odd parity wave magnetic state. The existence of the p-wave state with a single spin unpolarized line kx equals kz equals 0 in the kz equals 0 plane is enforced by the C2y symmetry. The DFT calculations show a spin unpolarized energy band for spin projections along the x and y axes and spin polarized energy bands for the spin projections along the z axes. The spin-splitting magnitude reaches tilde operator 200 MeV. The paper also discusses the resistive anisotropy of the material, which is a direct consequence of the unconventional p-wave magnetism. The transition from isotropic to anisotropic resistivity can serve as a signature for the transition to the magnetic phase, accessible by electrical measurements. In the realm of unconventional symmetry-breaking phases in p-wave magnets, a recent study has identified 73 material candidates for odd parity wave magnetism, featuring non-centrosymmetric magnetic crystal structures with C2 up TAC, T, symmetry. These materials are listed in the Supplementary Materials tab. And were found using the Mendata database. The study also discusses the concept of spontaneous resistive anisotropy ratio, which does not depend on the relaxation time, and its potential implications for understanding the physics of p-wave magnets. The research employs density functional theory to investigate the electronic structure of CeNiAsO, a material known for its p-wave magnetic phase below 7.6 K. By employing a tight-binding model Hamiltonian, the authors calculated the ohmic conductivity, demonstrating that the p-wave magnetic phase can be identified through its resistive anisotropy. This discovery is conceptually distinct from previous attempts to identify unconventional p-wave ordering via strongly correlated Fermi liquid instabilities or hidden orders. Moreover, the study highlights the importance of spin point groups in identifying p-wave magnets. It is shown that these groups can be used to sort material candidates into those with one spin unpolarized surface in the momentum space, and those with 3 spin unpolarized surfaces. The authors also discuss the analogy between p-wave magnetism and superfluid 3He, which has been elusive for many decades. They suggest that p-wave magnetism may open the possibility of its robust material realization, direct observation by photoemission spectroscopy, and device exploitation in metallic and insulating phases. The paper also provides details on the calculation of the longitudinal ohmic conductivity of the p-wave magnet CeNiAsO, utilizing the Pi-Procar version 5.6.6 for plotting spin-polarized energy bands and Fermi surfaces. The authors employed atom-centered Wannier functions within the VASP2 Wannier 90 code and calculated the ohmic conductivity as implemented in post-W90 code. They found that the longitudinal conductivity can be obtained as a function of the integral over the momentum space, with the integral being numerically evaluated using a fine momentum space mesh. Finally, the study concludes by discussing the implications of p-wave magnetism for understanding the physics of unconventional symmetry breaking phases. It emphasizes the potential for intriguing phenomena such as p-wave spin currents and the possibility to control the spin polarization by manipulating the direct space magnetic order. The research also connects the content of the 2 pages, showing the flow of ideas and identifying limitations, assumptions, and future work discussed.